The lattice structure of the semiconductor materials is crystalline. Let's look at some properties of the crystalline lattice. In week 2, we have already introduced its lattice properties. Crystalline silicon has a cubic diamond structure. A crystalline lattice means that atoms are arranged in a certain pattern, which repeats itself. A crystalline lattice has long-range order and symmetry. However, it does not mean that this pattern is the same in every direction. Or in other words, if we make a large cut through the lattice, the various planes you can make do not look the same. Here we see two planes of two different cuts in a crystalline silicon lattice, which originally consisted out of 3 by 3 by 3 unit cells. We see two important surfaces. The first one is referred to the 100 surface, and the normal of this plane points in the 100 direction. The silicon at the 100 surface always has two back bonds and two other valence electrons pointing to the front. The second surface is the 111 plane. It can be characterized by 3 silicon back bonds and 1 valence electron pointing in the normal to the plane. Why are these directions important? As we have discussed in week 3, we have direct and indirect band gap materials. This can be expressed in the so-called electronic band dispersion diagram. On the vertical axis you have the energy position of the valence and conduction band, and on the horizontal axis the crystal momentum, or in other words the momentum of the charge carriers. To be excited into the conduction band, the charge carriers in an indirect band gap material require a change in energy and in momentum. Here we see the real electronic band structure of the crystalline silicon. The white area reflects the energy levels in the forbidden band gap. The horizontal axis reflects the lattice momentum in various directions. The band gap of silicon is determined by the lowest energy point of the conduction band at X related to the 100 direction and the highest energy value of the valence band at gamma. Now we zoom into the band gap area. The band gap energy is the difference between those two levels and equals 1.12 electron volt, or 1107 nanometers, expressed in wavelengths. This transition is an indirect transition. I repeat again, the charge carriers need energy and momentum transfer to be excited. As you can see, crystalline silicon has a direct transition as well. However, this transition has an energy of 3.4 electron volts, which equals a wavelength of 364 nanometers. This is in the blue spectral part. For an indirect bandgap material, it's less likely that a photon above the bandgap is able to excite the electron into the conduction band in reference to a direct bandgap material. Consequently, the absorption coefficient of crystalline silicon in reference to direct bandgap materials like gallium arsenide and indium phosphide is significantly lower, as we can see in this plot. Crystalline silicon is indicated by the red line, whereas gallium arsenide and indium phosphide is indicated in yellow and green. You can see that in the visible spectrum, crystalline silicon absorbs less than the gallium arsenide and indium phosphide, but below 364 nanometers, it absorbs just as much as gallium arsenide and indium phosphide, because silicon has a direct band-to-band transition here as well. Germanium, indicated by the blue line, is like silicon. It is an indirect bandgap material. It has a bandgap of 0.67 electron volts, which means it already starts to absorb light at wavelengths below 850 nanometers. In the visible part, germanium has some direct transitions as well. Let's consider the design rules for solar cells as introduced in week 3. Let's start with spectral utilization. A band gap of 1.12 electron volts means that in theory we can generate a maximum short circuit current density of 45 milliamps per square centimeters using crystalline silicon. Let's consider the third design rule, light trapping. First, we look at a wavelength around 800 nanometers. Crystalline silicon has an absorption coefficient of 1000 per centimeter. You can simply calculate using Lambert's law that to realize an absorption of 90% of the light intensity at 800 nanometer, it requires an absorption path length of 23 microns. Around a wavelength of 970 nanometers, crystalline silicon has an absorption coefficient of 100 per centimeters, and it requires an absorption path length of 230 microns to absorb 90% of all the light. This is a typical thickness of silicon wafer. This demonstrates that the light trapping techniques become important for crystalline silicon absorber layers above a wavelength of 900 nanometers. Let's consider the last design rule, which is the utilization of the bandgap energy. As discussed in week 3, the bandgap utilization is determined by the recombination losses. As silicon is an indirect bandgap material, only Auger recombination and Shockley-Reed-Hall recombination will determine the open circuit voltage. If we consider Shockley-Reed-Hall, the recombination of charge carriers is related to the electrons trapped at defect states. In view of defects in the bulk of silicon, we can make a general difference between two types of silicon wafers: monocrystalline silicon and multicrystalline silicon, or also called polycrystalline silicon. Monocrystalline silicon, also called single crystalline, is a crystalline solid in which the crystal lattice is continuous, unbroken without grain boundaries over the entire solid up to the edges. In contrast, polycrystalline silicon, often abbreviated with polysilicon, is a material that consists of many small crystalline grains with random orientations. Between the grains, polysilicon has grain boundaries. Here you see two pictures of monocrystalline and multicrystalline wafers. Monocrystalline silicon wafer has one uniform color, whereas in multicrystalline silicon the various grains are clearly visible for the human eye. At the grain boundaries we find lattice mismatches. As a result, many defects reside at the grain boundaries. Consequently, the lifetime of charge carriers in polycrystalline silicon is shorter than for monocrystalline silicon due to the Shockley-Reed-Hall recombination. The more grain boundaries in the material, the shorter the lifetime of the charge carriers. It means that the grain size plays a role as well. In this figure from a paper of Bergman, we see the relation between the open circuit voltage of various solar cells developed over the world based on the multicrystalline wafers. On the horizontal axis, the average grain size of the multicrystalline silicon absorber layer is shown. The larger the grain size, the longer the charge carrier lifetimes, and the larger the bandgap utilization, and the larger the open circuit voltage will be. On the right you see now the open circuit voltages of various solar cells based on monocrystalline silicon wafers. As monocrystalline silicon has no grain boundary, much larger open circuit voltages can be obtained. The question now is, how do we make these types of silicon wafers? How do we make monocrystalline and how do we make multicrystalline wafers? We will discuss that in the next block.